Have you ever noticed how some places on Earth feel almost unreal, as if they were never meant to be seen at all? In this episode of Unearthed Secrets, we explore hidden depths, carved stone, bleeding ice, silent deserts, and volcanoes that still breathe. Landscapes shaped by time, pressure, and extremes. Before we begin, like and subscribe, and let us know in the comments where you're watching from and what time it is for you right now. The Eye Beneath the Sea. Far out in the Caribbean Sea, where the shallow turquoise waters of coral reefs suddenly give way to deep, almost black blue, there's a near-perfect circle cut into the ocean's surface. From the air, it looks deliberate, as if something massive pressed straight down into the sea and never lifted away. Boats slow as they approach it. Pilots point it out from above. Divers circle its edge with caution. This is the Blue Hole, one of the most striking marine formations on Earth, and one of the most misunderstood. The Great Blue Hole lies about 70 kilometers off the coast of Belize, near the center of Lighthouse Reef Atoll. It measures roughly 300 meters across, and plunges to a depth of more than 120 meters. Around it, the sea is shallow and alive with coral. Inside it, the water darkens quickly, swallowing light and obscuring depth. The transition is abrupt, and that sudden contrast is what gives the Blue Hole its unsettling presence. At first glance, it appears simple, a circular hole filled with deep water. But the Blue Hole is not just a void in the ocean floor. It is a layered record of Earth's past, carved by water long before the Caribbean Sea existed in its current form. To understand how the Blue Hole formed, it is necessary to imagine a very different world. During the last ice age, roughly 20,000 years ago, global sea levels were more than 100 meters lower than they are today. Vast amounts of water were locked away in continental ice sheets. Much of what is now seafloor was dry land. Lighthouse Reef, now submerged, was once a limestone plateau exposed to air, rain, and erosion. Over thousands of years, slightly acidic rainwater seeped into cracks in the limestone, slowly dissolving the rock. This process, known as karst erosion, created underground caves and chambers, similar to those found in places like the Yucatan Peninsula. These caves grew larger as water continued to flow through them. Stalactites formed on their ceilings, growing downward as mineral-rich water dripped slowly over centuries. The caves were dry, silent spaces, hidden beneath the land. Then the climate changed. As the Ice Age ended, glaciers melted and sea levels began to rise. The ocean advanced across the plateau, flooding the cave systems. Eventually, the roofs of some caves collapsed under their own weight, opening vertical shafts to the surface. When the sea finally stabilized at its modern level, these collapsed caverns became submerged sinkholes. The Blue Hole is one of the largest and most dramatic of these features. Its near-perfect circular shape is not a coincidence. It reflects the collapse of a roughly symmetrical cave chamber beneath the surface. Over time, erosion smoothed the edges, reinforcing the circle. Coral later grew around the rim, forming a bright ring that frames the dark interior. The structure of the Blue Hole is layered. Near the surface, the water is clear and oxygen-rich. Sunlight penetrates, allowing some marine life to exist near the rim. But this zone is thin. Descend deeper, and conditions change rapidly. At around 20 meters, light begins to fade. Colors dull. The bright reef fish disappear. The walls of the hole become steeper and darker. By 40 meters, the environment feels enclosed, even though the space is vast. Deeper still, around 90 meters, divers encounter one of the Blue Hole's most defining features, a layer of hydrogen sulfide. This toxic gas is produced by bacteria that thrive in oxygen-poor conditions, breaking down organic matter that sinks from above. The gas forms a cloudy, milky band that hangs in the water like fog. Passing through this layer feels like entering another world. Below it, the water is almost completely devoid of oxygen. Life becomes extremely sparse. The water is darker, heavier, and still. In this anoxic zone, decomposition slows dramatically. Organic material that sinks here does not break down in the usual way. This makes the Blue Hole an archive of sorts, preserving material that would otherwise disappear. Scientists study these layers to understand ancient ocean conditions and chemical processes that mirror those found in deep-sea environments. Embedded in the walls of the Blue Hole, deep below the surface, are massive stalactites, some more than 6 meters long. These formations are crucial evidence of the Blue Hole's past. Stalactites can only form in air-filled caves. Their presence confirms that this space was once dry land, long before the sea claimed it. The stalactites are tilted and broken, frozen in place by flooding and collapse. They don't grow anymore. They are geological fossils, marking the moment when air became water and land became sea. For centuries, the blue hole existed without global attention. Indigenous peoples navigated the surrounding waters, fishing and traveling among reefs and islands. The hole itself, far offshore, was likely known but not mythologized. It was simply part of the seascape. International recognition came much later in the 20th century, largely through exploration and media. In 1971, French oceanographer Jacques Cousteau brought the research vessel Calypso to the site. His team measured the depth, explored the interior, and confirmed its cave collapse origin. Cousteau later listed the Blue Hole as one of the world's top dive sites, a declaration that permanently changed its status. Tourism followed. Images of the Blue Hole from the air spread widely. The contrast between bright reef and dark center made it instantly recognizable. It became a symbol of Belize's marine environment and one of the most photographed natural features in the Caribbean. But fame brought misunderstanding. Despite its reputation, the Blue Hole is not a rich dive site in the traditional sense. There are few fish, little coral growth inside, and limited visual variety beyond the initial descent. What draws divers is not abundance, but depth, and depth is dangerous. The Blue Hole is one of the most hazardous recreational dive sites in the world. Its depth far exceeds standard diving limits. Nitrogen narcosis, oxygen toxicity, and decompression sickness are serious risks. The vertical walls provide no gradual ascent. Disorientation is common, especially in low light. Several divers have lost their lives here, often after exceeding planned depths or ignoring safety protocols. The hole offers no forgiveness for error. There are no ledges, no easy exits, no margins. Experienced guides emphasize restraint. Many recommend staying near the rim, observing the formation without attempting deep penetration. The deeper regions are better left to research teams using specialized equipment. From a scientific perspective, the Blue Hole is invaluable. Its stratified water layers provide insight into how oxygen-poor environments behave. Similar conditions exist in parts of the deep ocean and may have existed during periods of mass extinction in Earth's history. The hole also serves as a climate archive. By studying sediments and chemical markers within it, scientists can reconstruct past sea levels, temperatures, and biological activity. Each layer tells part of a long story written in darkness. The surrounding lighthouse reef adds another dimension. While the Blue Hole itself is relatively barren at depth, the reef around it is vibrant and diverse. Coral gardens, sharks, rays, and reef fish thrive just meters away from the void. This contrast is striking. Life presses right up to the edge of absence. The boundary between abundance and emptiness is sharply defined. From above, the Blue Hole appears calm and static. From below, it feels immense and consuming. Sound behaves differently. Light disappears. The sense of scale shifts. Many divers report a feeling of unease unrelated to physical danger, a psychological response to depth, darkness, and vertical space. The Blue Hole also challenges how people think about the ocean floor. It is not flat. It is not uniform. It contains cavities, scars, and collapses shaped by conditions that no longer exist. The hole is not an anomaly. It is a glimpse into processes that shape coastlines and seafloors worldwide, usually hidden from view. There's no mythic creature at the bottom, no lost city, no supernatural explanation. The Blue Hole's power lies in its reality. It exists because water dissolves rock, because sea levels change, and because structures collapse when support is removed. And yet, knowing this doesn't make it less unsettling. At sunrise, the Blue Hole darkens the surrounding water, absorbing the soft light of early morning. At midday, it appears almost black against brilliant turquoise. At sunset, shadows lengthen, and the circle becomes more pronounced, as if the sea itself were watching. At night, when boats leave and the reef quiets, the hole remains unseen but unchanged. Water continues to move slowly through it. Particles sink. Bacteria work. Chemistry unfolds without observation. The Blue Hole is not growing. It is not closing. It is a stable remnant of a vanished landscape. Its future depends on the same forces that shaped it: sea level, erosion, and time. Climate change introduces uncertainty. Rising sea levels, warming waters, and changing reef health could affect the balance of the surrounding ecosystem. The hole itself will likely persist, but the context around it may change. For Belize, the blue hole is both an asset and a responsibility. It draws attention, tourism, and scientific interest. It also demands protection, regulation, and respect. Overuse or careless access could disrupt fragile systems that have remained stable for thousands of years. For those who encounter it, whether from the air or the water, the blue hole leaves a lasting impression. It does not overwhelm with motion or noise. It overwhelms with absence, with depth, silence, and the suggestion of something beyond easy understanding. It is not a gateway. It is not an entrance. It is not an invitation. It is a reminder. A reminder that the surface of the earth hides vast histories beneath it, that the ocean is not just a horizontal plane, but a vertical world layered with chemistry, time, and collapse. That some of the most powerful features on the planet do not erupt or rise, but simply open and remain open. Off the coast of Belize, surrounded by life and light, the blue hole continues to hold darkness in perfect shape, an eye beneath the sea, unblinking, recording the passage of ages, quietly and without explanation. The stone carved by water. Along the remote edge of southern Chilean Patagonia, where mountains descend sharply into cold glacial water, there's a shoreline that looks less like rock and more like flowing paint frozen in motion. Walls curve inward, ceilings ripple overhead, and colors shift from deep blue to pale turquoise depending on the light. The stone appears soft, almost liquid, yet it is solid marble, sculpted not by tools or explosions, but by water working patiently over thousands of years. This is the Marble Caves, one of the most unusual geological formations on Earth. The Marble Caves, known locally as Cuevas de Mármol, Capilla de Mármol, and Catedral de Mármol, are located along the shores of Lake General Carrera, a massive glacial lake shared by Chile and Argentina. On the Argentine side, the same body of water is known as Lake Buenos Aires. It is one of the largest lakes in South America, stretching more than 180 kilometers in length and reaching depths of over 500 meters. What makes this lake unique is not only its size, but its water. Fed by glaciers descending from the northern Patagonian ice field, Lake General Carrera is filled with cold, mineral-rich meltwater. Suspended within it are fine particles of glacial silt, often called rock flour, which scatter light and give the water its signature blue-green color. This water is the key to the cave's existence and their appearance. The marble forming the caves began as limestone, deposited hundreds of millions of years ago when this region lay beneath an ancient sea. Layers of calcium carbonate settled on the seafloor, compacting over time into limestone. Later, intense heat and pressure associated with tectonic activity transformed the limestone into marble, recrystallizing its structure and increasing its hardness. For millions of years, this marble remained hidden beneath the surface, buried and unchanged. The transformation into the caves seen today began much later, after glaciers carved out the Patagonian landscape and meltwater filled the basin that became Lake General Carrera. Once the lake formed, wave action began its work. Unlike ocean waves driven by tides, lake waves are powered primarily by wind. In Patagonia, winds are frequent and strong, pushing water repeatedly against the shoreline. Over thousands of years, this constant motion eroded the marble cliffs at the waterline. Because marble dissolves slowly in slightly acidic water, chemical erosion combined with mechanical abrasion to carve smooth hollows into the rock. The process was gradual and precise. Areas of slightly softer marble wore away faster, creating cavities. As cavities deepened, wave energy became concentrated inside them, accelerating erosion. Over time, these hollows expanded into caves, tunnels, and arches. The marble caves didn't form all at once. They developed incrementally, shaped by fluctuating lake levels tied to glacial advance and retreat. When water levels were higher, erosion occurred at higher points on the rock. When levels dropped, erosion shifted downward. This created layered patterns and undulating forms that record the lake's changing height over thousands of years. The result is a series of interconnected caves and pillars rising directly from the water. Some formations stand alone like isolated columns. Others form cathedral-like chambers large enough to enter by boat. The ceilings are low and curved, following the contours carved by waves long ago. What gives the marble caves their most striking quality is color. The marble itself is primarily white and gray, streaked with darker veins, but the interior surfaces act like mirrors for the lake's water. Light reflects upward, tinting the stone with shades of blue, turquoise, green, and occasionally silver. The color shifts constantly. On cloudy days, the caves appear muted and gray-blue. In bright sunlight, they glow intensely, as if lit from within. When the lake is calm, reflections sharpen and the colors deepen. When wind disturbs the surface, the light fractures and patterns ripple across the walls. This interaction between water and stone creates the illusion that the marble is fluid. The rock appears to move, though it has not shifted in thousands of years. Despite their appearance, the marble caves are structurally fragile. Marble is harder than limestone, but still susceptible to erosion and fracture. The same forces that created the caves continue to reshape them. Small pieces break away, edges soften. Over geological time, the caves will eventually collapse or erode beyond recognition. Their current form is temporary, a snapshot in a long process of change. For most of human history, the caves were known only to local inhabitants. Indigenous peoples of Patagonia navigated these waters long before European exploration, using the lake as a route through rugged terrain. The caves were part of the landscape, not landmarks to be isolated or named. Wider. Recognition came in the 20th century as roads reached deeper into Patagonia and photography brought images of the caves to the outside world. Their visual impact quickly drew attention, and they became one of Chile's most iconic natural features. In 1994, the marble caves were declared a national monument of Chile, granting them legal protection. This status acknowledged both their geological significance and their vulnerability. Access to the caves is only possible by water. Visitors typically reach them by small boats or kayaks launched from nearby villages such as Puerto Rio Tranquilo. There are no walkways or platforms inside the caves. Entry depends entirely on lake conditions and water level. This dependence on water adds an element of uncertainty. During periods of high water, some caves become partially submerged and inaccessible. During low water, more of the marble pillars are exposed. The experience changes with the seasons and from year to year. Climate change has introduced additional variability. Glacial retreat alters water input into the lake, potentially affecting water level and sediment concentration. Changes in wind patterns could influence wave energy, subtly altering erosion rates. While these changes are slow, their cumulative effect could reshape the caves over time. The region around Lake General Carrera is sparsely populated. Harsh weather, rugged terrain, and isolation have limited development. This has helped preserve the caves, but increased tourism presents new challenges. Boat traffic, accidental contact, and pollution pose risks to the delicate surfaces. Conservation efforts focus on controlled access and awareness. Operators are encouraged to limit group sizes and avoid touching the rock. Even small amounts of oil from human skin can alter marble surfaces over time. Scientifically, the marble caves offer insight into chemical weathering in cold, freshwater environments, a process less studied than erosion in marine settings. The caves also preserve a record of lake-level changes, which can be used to reconstruct glacial history in Patagonia. The caves are not silent spaces. Sound behaves unusually inside them. Waves echo softly off curved walls. Voices carry and distort. Water dripping from the ceiling creates rhythmic patterns. These sounds reinforce the sense that the caves are active, even though their movement is imperceptibly slow. At night, when boats are gone and the lake is still, the caves fade into darkness. Without reflected light, their colors disappear, leaving only pale stone shapes against black water. The transformation underscores how dependent their appearance is on light and motion. The marble caves do not dominate the landscape through size or height. Their power lies in intimacy. They are close, enclosing, and immersive. Visitors do not observe them from afar. They move through them, surrounded by stone shaped by water. There are no myths carved into the walls, no inscriptions, no signs of ancient construction. The caves carry no direct human history. Their story is entirely geological, written in curves rather than lines. Yet they evoke comparisons to architecture, cathedrals, chapels, halls, because the human mind searches for familiar patterns. The resemblance is accidental. Nature did not imitate design. Design imitates nature. Over long periods, the marble caves will change. Water will continue to dissolve stone. Pillars will thin. Ceilings will collapse. New forms may emerge as others disappear. What exists today will not exist forever. This impermanence is part of their significance. They demonstrate how beauty can arise from slow erosion rather than construction, from subtraction rather than addition. In Patagonia, where glaciers grind mountains into dust and lakes carry that dust away, the marble caves stand as a meeting point between solidity and motion. Stone meets water, light meets surface, time meets patience. They do not roar like waterfalls or erupt like volcanoes. They whisper, shaped by repetition rather than force. Each wave removes a fraction of a millimeter. Each reflection paints the walls anew. Standing at the entrance to one of these caves, surrounded by blue water and white stone, it becomes difficult to separate land from lake. The boundary dissolves. Everything feels connected, fluid, and transitional. The marble caves are not monuments to endurance. They are monuments to process. And as long as glacial water continues to lap against marble shores in southern Chile, the stone will continue to yield, quietly, steadily, becoming something new without ever announcing the change. The ice that bleeds. At the edge of one of the coldest, driest deserts on Earth, a glacier spills what looks like blood onto pristine white ice. The color is deep, rust red, streaking downward from a crack in the frozen surface and spreading slowly across the glacier below. Against the blinding white of Antarctica, the contrast is shocking. It looks like an injury in the ice itself, raw, fresh, and deeply unsettling. This phenomenon is known as blood falls, and despite its appearance, it is neither a sign of life nor death, but the result of chemistry, isolation, and time operating in extreme conditions. Blood Falls emerges from the Taylor Glacier, located in the McMurdo Dry Valleys of Antarctica. These valleys are among the most unusual environments on the planet. Unlike much of Antarctica, they are largely free of ice and snow, shaped by katabatic winds that descend from the polar plateau and evaporate moisture almost instantly. Rain is virtually non-existent. Temperatures remain well below freezing for most of the year. The landscape is barren, rocky, and silent. Within this environment, Taylor Glacier flows slowly from the East Antarctic ice sheet toward Lake Bonny, a permanently ice-covered lake trapped in the valley. The glacier moves at a rate of only a few meters per year, grinding forward under its own immense weight. It is from a fissure near the glacier's terminus that Blood Falls pours outward. At first discovery, the phenomenon defied explanation. Blood Falls was first observed in 1911 by Australian geologist Thomas Griffith Taylor during the British Antarctic expedition led by Robert Falcon Scott. Taylor noticed the red staining on the ice and initially suspected that it might be caused by red algae, similar to organisms known to color snow in other parts of the world. At the time, this explanation seemed reasonable. Biology was often invoked to explain unexpected color in natural environments. However, as research advanced, this idea was gradually discarded. The true explanation turned out to be far more complex and far more revealing about the hidden world beneath Antarctica's ice. The red color of Blood Falls comes from iron-rich water emerging from beneath the glacier. When this water reaches the surface and comes into contact with oxygen, the iron oxidizes, much like rust forming on exposed metal. The result is a deep red-brown coloration that stains the ice and gives the illusion of flowing blood. But the source of this water is what makes Blood Falls extraordinary. Beneath Taylor Glacier lies a subglacial brine reservoir, a body of liquid water trapped beneath hundreds of meters of ice. This water is hypersaline, meaning it contains extremely high concentrations of salt, far saltier than seawater. This salinity prevents the water from freezing, even at temperatures far below zero. The brine is ancient. Scientists estimate that this water has been isolated from the surface for more than 1 million years. Originates from a time when the McMurdo Dry Valleys were flooded by an ancient ocean. As the climate cooled and glaciers advanced, seawater became trapped beneath the ice. Over time, salts concentrated as ice formed above, leaving behind a dense, mineral-rich brine sealed away from the outside world. For hundreds of thousands of years, this water remained hidden, under pressure, in total darkness. As Taylor Glacier slowly moves and deforms, cracks form within the ice. Thus, fractures act as channels, allowing the pressurized brine to escape. When it reaches the surface, it spills out onto the glacier face, creating blood falls. The flow is not constant. It pulses slowly, responding to changes in pressure within the glacier and seasonal temperature shifts. Sometimes the falls appear active and vivid. At other times, they fade, darken, or nearly disappear, only to return later. Despite its dramatic appearance, Blood Falls is not warm. The water emerges cold, near freezing, but still liquid due to its salt content. It moves sluggishly, thickened by its density, spreading slowly across the ice rather than splashing or cascading like a traditional waterfall. What makes Blood Falls scientifically remarkable is not just the chemistry, but the biology hidden within the brine. In 2009, researchers made a discovery that transformed understanding of the site. They found that the brine contains a living microbial ecosystem, microorganisms that have survived in complete isolation, without sunlight, for immense periods of time. These microbes do not rely on photosynthesis. Instead, they survive through chemosynthesis, using chemical reactions involving iron and sulfur to generate energy. In this dark, oxygen-poor environment, iron becomes central to metabolism. The microbes convert ferric iron to ferrous iron, a process that sustains them, but also contributes to the chemical composition of the brine. This discovery was groundbreaking. It demonstrated that life can survive in conditions previously thought too extreme: sub-zero temperatures, high salinity, complete darkness, and long-term isolation. Blood Falls became one of the most compelling analogs for potential extraterrestrial life, particularly on icy moons such as Europa or Enceladus, where subsurface oceans may exist beneath thick ice shells. The McMurdo Dry Valleys themselves are often described as the closest terrestrial equivalent to the surface of Mars. They are cold, dry, and exposed to intense radiation. The presence of a hidden, living ecosystem beneath Taylor Glacier suggests that similar systems could exist elsewhere in the solar system, protected beneath ice from hostile surface conditions. Blood Falls, therefore, is not just a curiosity. It is a window into deep time and extreme survival. The chemistry of the brine is equally revealing. In addition to iron, it contains high levels of chloride, sulfate, and other dissolved minerals. The lack of oxygen in the system prevents iron from oxidizing underground. Only when the brine reaches the surface does oxidation occur, producing the red coloration. This delayed reaction is why the water appears clear or slightly yellowish as it emerges, then rapidly turns red as it flows across the ice. The process is slow, methodical, and unrelenting, much like the glacier itself. From a distance, Blood Falls appears violent or alarming. Up close, it is quiet. There is no roar, no rush of water, only a slow seep, staining ice that will eventually carry the iron-rich residue forward as the glacier advances. Over time, the stained ice is buried, fractured, or sublimated away, and the surface resets, but the source remains beneath, waiting for pressure to release it again. Studying Blood Falls is logistically difficult. The site is remote, accessible only by helicopter during brief Antarctic summer windows. Temperatures are extreme. Equipment must function in cold that breaks plastics and drains batteries. Contamination must be avoided to preserve the pristine nature of the microbial ecosystem. As a result, research is slow and deliberate. What scientists have learned so far continues to reshape assumptions about where life can exist. The microbes beneath Taylor Glacier have likely survived multiple ice ages, adapting without sunlight, fresh nutrients, or contact with the surface world. They exist in a closed system, recycling limited resources over geological timescales. This resilience challenges the idea that life requires stable, temperate conditions. Instead, Blood Falls suggests that life can persist wherever chemistry allows energy to flow, even in isolation. There are no legends associated with Blood Falls. No indigenous stories. Antarctica has no native human population. Its meaning comes not from culture, but from science and symbolism imposed afterward. Yet the visual impact is unavoidable. Blood Falls looks wrong. It violates expectations. Ice is supposed to be clean, white, and inert. Blood Falls suggests injury, motion, and exposure. It feels like something hidden has been revealed unintentionally. That reaction is deeply human, but the ice is not wounded. It is communicating. Blood Falls tells a story of trapped oceans, shifting glaciers, and microbial persistence. It reveals that Antarctica is not a dead continent, but a dynamic system with a hidden circulation beneath its frozen surface. It also raises questions about change. As global temperatures rise, Antarctic ice systems are under increasing stress. Glaciers thin, meltwater pathways shift. Subglacial systems that have been stable for millennia may change in unpredictable ways. Blood falls could become more active or disappear entirely, depending on how ice dynamics evolve. For now, it remains. A rust-colored scar on white ice, a chemical signal from a buried world, a reminder that even the most lifeless-looking environments may hide complexity beneath. Blood Falls does not flow fast. It does not spread far. It does not seek attention. And yet, it has become one of the most iconic images of Antarctica. Not because it is large, but because it reveals something unexpected. In a place defined by cold and stillness, Blood Falls shows that the Earth never fully stops. Beneath ice kilometers thick, water moves. Chemistry reacts. Life endures. The glacier will continue to creep forward. The brine will continue to press upward. The iron will continue to oxidize when exposed to air. And the ice, when it bleeds again, will remind us that the most extreme places on Earth are not empty. They are simply quiet, waiting to be understood. The canyon carved by light. In the high desert of northern Arizona, hidden beneath an unassuming stretch of land, there's a canyon so narrow that sunlight enters only in fragments. When it does, the light bends, scatters, and settles across stone in ways that feel deliberate, almost staged. Walls ripple like fabric. Shadows curve instead of falling straight. Dust drifts through beams of light, suspended as if time has slowed. This is Antelope Canyon, a place shaped not by force alone, but by patience, repetition, and the quiet work of water guided by gravity. The Antelope Canyon is located near the town of Page, Arizona, on Navajo Nation land. It is one of the most famous slot canyons in the world, yet its origins are entirely unremarkable in the geological sense. There was no massive earthquake here, no volcanic eruption, no sudden collapse. Antelope Canyon exists because rainwater, sand, and stone interacted in the same way, again and again, over thousands of years. To understand Antelope Canyon, it's necessary to understand slot canyons themselves. Slot canyons form in regions where sandstone is present, rainfall is infrequent but intense, and terrain allows water to concentrate into narrow paths. When flash floods occur, water rushes through cracks and shallow channels, carrying sand and debris that act as natural abrasives. Over time, these floods carve deep, narrow passages into the rock. The sandstone that makes up Antelope Canyon belongs primarily to the Navajo Sandstone Formation, deposited around 190 million years ago during the early Jurassic period. At that time, this region was a vast desert, covered in enormous sand dunes, comparable to those found in today's Sahara. Wind piled sand into towering formations, which later hardened into stone under pressure and mineral cementation. For millions of years, this sandstone remained intact, buried, and unmoving. The transformation into Antelope Canyon began much later, as uplift and erosion exposed the rock to surface conditions. Rainfall, rare but powerful, found weaknesses in the stone and exploited them. Flash floods are the defining force behind Antelope Canyon. Unlike rivers that flow continuously, flash floods occur suddenly, often far upstream, with little warning. Water funnels into narrow spaces, accelerating as it moves. In a slot canyon, this concentrated energy scours the walls and floor with immense force, even if the flood lasts only minutes. Each flood removes a thin layer of rock. One event alone does little. Thousands of events, spread across centuries, reshape entire landscapes. Antelope Canyon is divided into two primary sections: Upper Antelope Canyon and Lower Antelope Canyon. Upper Antelope Canyon, known in Navajo as Tsebeganilini, meaning the place where water runs through rocks, is the more accessible and widely photographed section. Lower Antelope Canyon, called Hasdistazi or Spiral Rock Arches, is narrower, steeper, and more physically demanding to navigate. Upper Antelope Canyon is famous for its light beams, shafts of sunlight that penetrate the canyon during certain times of day, typically around midday in late spring and summer. These beams occur when sunlight enters the canyon at a steep angle and reflects off airborne dust, making the light itself visible. The effect is fleeting and highly dependent on timing, weather, and season. A slight shift in the sun's position can erase the beams entirely. Clouds can soften them. Wind can disperse dust. When conditions align, however, the canyon appears illuminated from within. Lower Antelope Canyon lacks the same dramatic beams, but compensates with complexity. Its passages twist more tightly. Stairways and ladders are required to move through it. Light enters indirectly, bouncing multiple times before reaching the floor. This produces softer gradients of color and deeper shadow. The colors of Antelope Canyon are not applied by light alone. They are embedded in the stone. The sandstone contains iron oxides and other minerals that give it hues of red, orange, pink, and gold. As light moves across the curved walls, these colors intensify or fade, creating the illusion that the rock itself is glowing. The canyon walls are smooth and sculpted, shaped by water carrying sand that polishes the surface. Vertical grooves, scallops, and wave-like forms record the direction and force of past floods. In some places, the rock narrows to less than a meter across. In others, it opens briefly before closing again. Despite its serene appearance in photographs, Antelope Canyon is a dangerous place. Flash floods remain a real and ongoing threat. Rain falling miles away can send walls of water racing through the canyon with little warning. Because slot canyons are so narrow, there's nowhere for the water to spread out. Levels can rise rapidly, filling passages completely. In 1997, a flash flood in Lower Antelope Canyon killed 11 people, most of them tourists. The tragedy fundamentally changed how the canyon is managed and accessed. Since then, safety protocols, weather monitoring, and guided access have become mandatory. Today, visitors are only allowed to enter Antelope Canyon with authorized Navajo guides. Tours are carefully timed. Weather is monitored constantly. Even so, access can be closed suddenly if conditions upstream are deemed unsafe. These measures reflect respect for both the land and its risks. For the Navajo people, Antelope Canyon is more than a geological feature. It holds cultural and spiritual significance. The flowing forms of the canyon are seen as alive, shaped by forces that deserve respect. Stories and traditions connected to the land emphasize balance, awareness, and humility in the presence of nature. The commercialization of Antelope Canyon has brought economic opportunity to the Navajo Nation, but it has also raised concerns about preservation. Foot traffic introduces wear. Dust from shoes alters the canyon floor. Noise disrupts the natural acoustics of the space. To mitigate these impacts, access is limited, pathways are controlled, and visitors are instructed not to touch the walls. Even slight contact can transfer oils that darken the sandstone over time. Scientifically, Antelope Canyon provides insight into erosion dynamics in arid environments. Its precise shapes reveal how water behaves under extreme confinement. The canyon is also studied as an example of rapid landscape evolution on a geological timescale. Fast compared to mountain building, slow compared to human lifespans, the canyon continues to change. Each flash flood alters its shape slightly. Walls shift, floors deepen. Features visible today may vanish or transform within decades. The canyon photographed in the 1980s is not identical to the one seen today. This impermanence is central to its significance. Antelope Canyon is not a finished object. It is a process. Light plays a role not only in perception, but in meaning. The canyon is most famous for how it looks when illuminated, yet most of its existence occurs in shadow. For much of the day, light is indirect, reflected, softened. The dramatic moments are brief. This mirrors the canyon's formation. Rare events, floods, do the most work. Long periods of stillness separate them. Sound behaves unusually inside Antelope Canyon. Voices echo softly. Footsteps reverberate. Wind passing overhead can be heard faintly through the rock. During quiet moments, the canyon feels enclosed, insulated from the desert above. Temperature inside the canyon is often cooler than outside, providing brief relief from the Arizona heat. This microclimate further emphasizes the canyon's separation from the surface world. Despite its fame, Antelope Canyon was largely unknown to the wider world until the late 20th century. Improved roads, photography, and tourism brought it into the global imagination. Images circulated widely, often without context, presenting the canyon as timeless and static. In reality, it is neither. The canyon owes its existence to vulnerability. Rock soft enough to be carved, rainfall unpredictable enough to concentrate force, terrain shaped to guide water downward. Change is built into its structure. Climate change introduces new uncertainty. Altered rainfall patterns could increase or decrease flood frequency. More intense storms could accelerate erosion or increase danger. Drier conditions could slow the canyon's evolution, but also alter dust and light conditions. The future shape of Antelope Canyon is unknown, as it always has been. At sunrise, light enters the canyon at shallow angles, grazing the walls and revealing subtle textures. At midday, beams appear briefly. At sunset, the canyon darkens, holding on to warm tones before fading into shadow. At night, the canyon is closed and silent. Stars pass overhead, unseen from below. The rock cools, dust settles, the canyon waits. Antelope Canyon is often described as beautiful, but beauty is not its primary function. It exists because water needed somewhere to go. It persists because sandstone yields slowly rather than breaking suddenly. It captivates because humans respond deeply to light, interacting with form. There are no inscriptions on the walls, no markers of ancient occupation within the canyon itself. Human presence is temporary here. The canyon does not remember footsteps, it remembers water. Each curve is a record of flow. Each narrowing marks acceleration. Each widening marks release. The canyon is a frozen motion, shaped by events that no one witnessed directly. Standing inside Antelope Canyon, it becomes clear that the most powerful forces shaping Earth are not always loud or fast. Sometimes they are intermittent, focused, and precise. A flood that lasts minutes can carve stone that lasts centuries. A shaft of light that lasts seconds can define how a place is remembered. Antelope Canyon does not ask to be conquered or solved. It asks to be observed carefully, entered briefly, and left intact. In the Arizona desert, beneath a surface that gives no hint of what lies below, water continues to wait for its moment. And when it comes, the canyon will change again. Quietly, decisively, reshaping walls that already look impossibly smooth. The canyon carved by light is, in truth, carved by water. Light simply reveals what patience has already done. The forest that time forgot. In the heart of the Namib Desert, surrounded by some of the tallest sand dunes on Earth, there's a place where trees stand frozen in death. Their branches reach upward, twisted and blackened, casting sharp shadows across a white clay floor. There are no leaves, no birds perch in the branches, no sound of water or wind moving through foliage. The trees have been dead for centuries, yet they have not fallen, rotted, or turned to dust. This place is Deadvlei, a landscape where time appears to have stopped, and decay itself seems suspended. The Deadvlei lies within the Namib-Naukluft National Park, near the more widely known Sossusvlei, in western Namibia. The surrounding dunes rise more than 300 meters high, towering over the flat basin below. Their color shifts with the light, from deep red to glowing orange, while the floor of Deadvlei remains pale and cracked, almost reflective in the sun. The contrast is extreme and immediate. Red sand, white earth, black trees, blue sky. At first glance, Deadvlei looks artificial, as if staged. But every element here is the result of natural processes operating over thousands of years, driven by climate change, shifting sands, and the disappearance of water. The story of Deadvlei begins with a river. Thousands of years ago, the Taukab River flowed intermittently through this region, carrying water from the Naukluft Mountains toward the Atlantic Ocean. During wetter climatic periods, the river flooded regularly, filling shallow basins between dunes and supporting vegetation. One of these basins became Deadvlei. At that time, Deadvlei was not dead. It was a shallow wetland. Camel thorn trees, Vachellia areoloba, took root along the basin's edge and within it. These trees are exceptionally hardy, capable of surviving in arid conditions by growing deep root systems that tap into groundwater. With seasonal flooding, the area supported grasses, shrubs, and animal life. For a time, Deadvlei was a functioning ecosystem. Then the climate changed. As the region became drier, rainfall decreased, and flooding became less frequent. At the same time, wind-driven sand dunes began migrating across the landscape. The Namib Desert is one of the oldest deserts on Earth, and its dunes are dynamic structures constantly reshaped by wind. Eventually, dunes encroached on the Sakab River's course, blocking its flow. Water could no longer reach Dedvle. The basin dried out completely, cutting off the trees from their only reliable source of moisture. The trees died where they stood, but they did not decompose. Normally, dead wood rots as bacteria, fungi, and insects break it down. In Dedvle, those processes could not occur. The environment was too dry. There was virtually no moisture to support decomposition. Termites could not survive. Microbial activity was minimal. Instead of rotting, the trees dried out. Over centuries, intense sunlight and heat baked the wood, slowly carbonizing it. The trees turned dark, almost black, but they didn't burn. They hardened. Their structure remained intact, preserved by the absence of decay, rather than by freezing or burial. Radiocarbon dating suggests that many of the trees in Dedvle are more than 600 to 900 years old. Some may be even older. They have stood motionless through centuries of shifting dunes, climate fluctuations, and human history elsewhere on the planet. The ground beneath them tells a parallel story. The basin floor is composed of clay deposited by ancient floodwaters. When wet, clay is soft and sticky. When dry, it contracts and cracks. In Dedvle, the clay has been dry for centuries. The result is a pale, cracked surface that reflects sunlight intensely. This white clay pan contrasts sharply with the surrounding dunes, which are rich in iron oxide, giving them their deep red color. The dunes themselves are among the highest in the world, some exceeding 300 meters. They encircle Dedvle, isolating it visually and physically. The name Dedvle comes from Afrikaans, meaning dead marsh. The term is descriptive rather than symbolic. Nearby, Sossusvlei, meaning dead-end marsh, still occasionally fills with water during rare floods. Dedvle does not. It is permanently cut off. The visual impact of Dedvle is amplified by light. In the early morning and late afternoon, shadows stretch long and sharp across the clay. The black trees become silhouettes against glowing sand. At midday, the light is harsh and unforgiving, flattening shadows and intensifying contrast. The heat becomes overwhelming. Despite its appearance, Dedvle is not completely lifeless. Microorganisms exist within the clay. Insects pass through. Birds occasionally cross overhead. But there's no sustained ecosystem here. Life does not settle. It passes by. For indigenous peoples, the wider region of the Namib Desert has long been known and navigated. The harshness of the environment shaped nomadic movement, survival strategies, and respect for water sources. Dedvle itself was never a settlement. Its lack of water made it unsuitable for habitation, even when other areas supported life. Modern recognition of Dedvle came relatively late. Its remote location and extreme conditions limited access. It became widely known through photography, which captured the stark geometry of its elements. Images of Dedvle often circulate without context, appearing surreal or symbolic. In reality, Dedvle is not symbolic. It is literal. It shows what happens when water disappears permanently from a system that once depended on it. It shows preservation through absence rather than protection. It shows how landscapes can become archives, holding physical evidence of past conditions long after those conditions have vanished. Scientifically, Dedvle provides insight into desertification, dune dynamics, and long-term climate shifts. It illustrates how river systems can be disrupted by sediment movement and how ecosystems collapse when thresholds are crossed. The camelthorn trees themselves are valuable records. Their growth rings, though difficult to analyze due to drying, offer clues about past rainfall patterns. Their survival as physical structures demonstrates how extreme aridity can preserve organic material for extraordinary lengths of time. Unlike fossils, these trees are not mineralized. They remain wood. If moisture were introduced, decay could resume. Their preservation is conditional, dependent on continued dryness. This fragility contrasts with their apparent permanence. Climate change adds uncertainty to Dedvle's future. While the Namib Desert remains arid, changes in rainfall patterns or extreme weather events could alter conditions. A significant flood could deposit sediment, bury trees, or even introduce moisture that accelerates decay. Conversely, increased aridity could further stabilize the site. Tourism has brought both awareness and risk. Visitors walk among the trees, drawn by the desire to stand within a landscape that feels unreal. Foot traffic can damage the clay pan, leaving footprints that take years to fade. Touching the trees can weaken their surface. Conservation measures aim to balance access with preservation. There are no fences around the trees, no barriers separating observer from object. The openness reinforces the sense that this is not a museum display, but an exposed moment in Earth's history. Sound behaves differently in Deadvley. The dunes block wind. The open pan offers no echo. Silence feels heavy, broken only by footsteps on dry clay or distant wind across sand ridges. The absence of water sound is notable. In a place shaped by the loss of water, silence replaces flow. At night, Deadvley becomes something else entirely. Temperatures drop sharply. The sky fills with stars, unfiltered by humidity or light pollution. The trees stand as black cutouts against the Milky Way. The dunes fade into shadow. The clay pan reflects faint starlight. In these moments, the age of the place becomes more apparent. The trees predate modern borders, modern languages, and much of recorded history. They have outlasted civilizations, technologies, and climates elsewhere, yet they are not monuments. No one placed them here intentionally. They were simply left behind. Deadvley is often described as haunting, but it is not hostile. It does not threaten. It does not erupt or collapse. Its impact comes from stillness and contrast. Red dunes that move, white clay that cracks, black trees that do neither. The scene appears static, but it is not. Dunes continue to migrate slowly. The pan continues to expand and contract with temperature. The trees continue to weather imperceptibly. Time is present here, but it moves differently. There is no regeneration cycle, no visible succession. Deadvley does not heal or recover. It records. Standing in Deadvley, it becomes clear that deserts are not empty. They are selective. They preserve some things while erasing others. They strip systems down to essentials and then remove even those. Deadvley exists because multiple processes aligned. A river changed course, dunes advanced, climate dried, decay stopped. Remove any one of these and the place would not exist as it does today. That convergence is what makes Deadvley rare. It is not just a dead forest. It is a moment captured between life and disappearance, held in place by dryness and light. As long as the Namib remains arid, the trees will continue to stand. They will not grow. They will not fall. They will simply remain, dark outlines against shifting sand. In the Namib Desert, where some landscapes are constantly remade by wind, Deadvley offers the opposite, a place where change stopped just long enough for history to remain visible, a forest that did not decay, a marsh that never returned, a reminder that absence can preserve as powerfully as presence. And in that stillness, Deadvley tells one of the clearest stories the desert has to offer, not of survival, but of what happens when survival quietly ends, and the land chooses to remember instead. The volcano that never sleeps. In eastern Java, where the land rises and falls in layers shaped by fire, there's a volcano that announces itself not through size, but through presence. Smoke drifts continuously from its crater. The ground beneath it is gray, powdery, and vast, stretching outward like an empty ocean. Surrounding it is a ring of mountains forming a natural amphitheater, enclosing the scene in silence and scale. This is Mount Bromo, one of Indonesia's most active and closely watched volcanoes, and one of the most unusual volcanic landscapes on Earth. The Mount Bromo rises from within the Tengger caldera, a massive volcanic depression measuring roughly 10 kilometers across. Unlike towering stratovolcanoes that dominate their surroundings, Bromo stands relatively low, reaching about 2,329 meters above sea level. Yet it commands attention because it sits inside a far larger structure, one shaped by catastrophic eruptions long before human memory. The Tengger caldera is the remnant of an ancient volcano that once stood far taller than anything visible today. Tens of thousands of years ago, that volcano erupted violently, emptying its magma chamber and collapsing inward. What remained was a wide, bowl-shaped depression, later partially filled by ash, lava, and sediment from subsequent eruptions. Within this caldera lies the Sea of Sand, a flat, ash-covered plain that surrounds Mount Bromo, and several neighboring volcanic cones. This feature alone sets Bromo apart. Instead of forests or lava fields, the volcano rises from a desert-like expanse of fine volcanic sand, gray and lifeless, constantly reshaped by wind. The Sea of Sand is not truly sand in the conventional sense. It is composed primarily of volcanic ash and fine tephra, particles ejected during eruptions and ground down over time. The surface feels soft underfoot but compacted in places, bearing footprints, horse tracks, and vehicle marks that fade slowly in the dry air. At the center of this barren plain, Mount Bromo emits a steady plume of sulfur-rich gas. The smell is sharp and unmistakable. The sound is constant, a low hiss rising from the crater, punctuated occasionally by deeper rumbles from below. Mount Bromo is part of the Bromo-Tengger-Semeru National Park, a protected area that includes multiple volcanoes, forests, and highland ecosystems. Just beyond the caldera rim, vegetation returns abruptly. Pine forests, grasslands, and agricultural terraces cling to the slopes, highlighting the stark boundary between fertile land and volcanic emptiness. This contrast is not accidental. Volcanic soil is among the most fertile on Earth once it stabilizes. Ash deposits enrich the ground with minerals, supporting dense agriculture in surrounding regions. Yet inside the caldera, constant activity prevents life from gaining a foothold. The ground is too unstable, too dry, and too frequently disturbed. Mount Bromo's activity is persistent rather than explosive. It does not remain dormant for centuries before erupting violently. Instead, it vents gas almost continuously and produces small to moderate eruptions at irregular intervals. Ash plumes rise hundreds or thousands of meters into the air, sometimes disrupting air travel and coating nearby villages in gray dust. These eruptions are usually strombolian or phreatic in nature, driven by gas pressure and interaction between magma and groundwater. Lava flows are rare. The danger comes from ash, falling debris, toxic gases, and sudden explosive bursts. The crater itself is accessible by climbing a staircase built along the rim. From above, the opening appears wide and raw, its interior walls coated in sulfur deposits and fresh ash. Looking down, visibility shifts with wind and gas. At times, the crater seems shallow. At others, it disappears into steam and shadow. Despite the risks, people have lived alongside Mount Bromo for centuries. The Tenggerese people, an indigenous group believed to be descendants of the Majapahit Empire, inhabit villages along the caldera's rim and surrounding highlands. Their culture, language, and traditions are distinct within Java, shaped by isolation and proximity to the volcano. For the Tenggerese, Mount Bromo is not merely a geological feature, it is sacred. According to local belief, Bromo is the dwelling place of deities, and its activity reflects a balance between humans and the natural world. This belief is most clearly expressed during the Yadnya Kasada festival, held annually. During this ritual, Tenggerese villagers gather at the volcano to offer sacrifices: rice, fruit, vegetables, livestock, and other goods, thrown directly into the crater. The ceremony traces its origin to a legend involving a royal couple who prayed to the gods for children. When their prayers were answered, they were instructed to sacrifice their youngest child to the volcano. Instead, offerings were given, establishing a tradition meant to maintain harmony. To outsiders, the ritual appears dangerous and symbolic. To the Tenggerese, it is practical and necessary, a way of acknowledging the volcano's power and ensuring continued balance. Occasionally, individuals attempt to retrieve offerings from the crater walls, risking their lives in the process. Accidents have occurred, reinforcing the reality that reverence does not eliminate danger. From a scientific perspective, Mount Bromo provides valuable insight into open vent volcanic systems. Unlike volcanoes that seal themselves between eruptions, Bromo's crater remains open, allowing gas to escape continuously. This reduces pressure buildup but does not eliminate eruption risk. Monitoring stations around the volcano track seismic activity, gas emissions, and ground deformation. These data help predict eruptions, though forecasting remains imprecise. Bromo's behavior can change rapidly, shifting from quiet degassing to explosive activity within days or even hours. The broader volcanic complex includes Mount Batok, an extinct cone, and Mount Semeru, Indonesia's highest and one of its most active volcanoes. Semeru rises beyond the caldera, erupting frequently and sending ash plumes skyward. Together, these peaks form a dynamic volcanic system driven by the subduction of the Indo-Australian Plate beneath the Eurasian Plate. Indonesia sits along the Pacific Ring of Fire, a zone of intense tectonic activity. More than 130 active volcanoes dot the archipelago. Mount Bromo is one of the most accessible, making it both a scientific asset and a public hazard. Tourism has transformed the region dramatically. Sunrise viewpoints along the caldera rim attract visitors from around the world. At dawn, the sea of sand fills with mist, and volcanic cones emerge like islands. As the sun rises, light reveals layers of ash, ridges, and smoke, creating one of the most photographed scenes in Southeast Asia. Jeep tracks crisscross the caldera floor, horses carry visitors toward the crater. Infrastructure has expanded to accommodate demand. With this growth comes pressure on the environment, on safety systems, and on local communities. Authorities periodically restrict access during heightened activity. Masks are distributed when ash levels rise. Warning zones expand and contract depending on volcanic conditions. Despite precautions, Bromo remains unpredictable. The volcano's persistence affects daily life. Ashfall can destroy crops. Sulfur gas irritates lungs and eyes. Roads close. Flights divert. Yet life continues. Farmers replant. Rituals proceed. The volcano remains central rather than peripheral. At night, Mount Bromo changes character. The crowds leave. Temperatures drop sharply. Gas plumes glow faintly under moonlight. The hiss from the crater becomes more pronounced in the silence. The sea of sand darkens into a featureless plain. The sense of scale deepens. The caldera walls loom overhead. The volcano feels less like a destination and more like a presence, awake, breathing, waiting. Mount Bromo is not the largest, nor the most violent, nor the most destructive volcano in Indonesia. Its significance lies elsewhere. It is a reminder that volcanic activity does not always announce itself with catastrophe. Sometimes it persists quietly, shaping land and culture over generations. Geologically, the mountain will change. The crater will widen or collapse. Eruptions will deposit new layers of ash. The sea of sand will deepen and shift. Over long periods, vegetation may reclaim parts of the caldera, only to be erased again by renewed activity. For now, Mount Bromo remains exposed. Its process is visible, its dangers known, its rhythms accepted. It is a volcano that never truly sleeps. It exhales continuously, releasing pressure without closing itself off. It reminds those who live near it that stability is temporary and balance must be maintained. In eastern Java, surrounded by silence, smoke, and stone, Mount Bromo stands not as a monument to destruction, but as a lesson in coexistence, between fire and land, between belief and science, between human life and the restless earth beneath it. As this journey comes to an end, these places remain, quiet, powerful, and unchanged by our passing. They remind us that the earth is still shaping itself, far beyond human timelines. Thank you for watching Unearthed Secrets. Until next time, keep looking closer beneath your feet.